So, what if I told you that a whole year before anyone even set foot on the moon, engineers had already drafted a super detailed plan to send people to Mars, Venus, and even all the way out to Jupiter? Okay, let's get right into it. What you're looking at here is the cover of a report from way back in January 1968. NASA commissioned it, and a company called North American Rockwell put it together. And while the whole world was glued to the TV watching the race to the moon, these folks were tasked with looking way, way beyond that, to the next giant leap for humanity. You have to understand, the whole point of this study was just mind-blowingly ambitious. This wasn't about planning just one mission to one planet. No. This was about figuring out all the common tech needed for a whole family of manned missions across the solar system. They were basically trying to draw the entire roadmap all at once. And just look at this list of places they were aiming for. We're not talking about just planting a flag on Mars. These engineers were seriously crunching the numbers for crewed missions to Mercury, to Venus, to the huge asteroids Vesta and Ceres, and even a trip to Ganymede, Jupiter's biggest moon. I mean, the sheer scale of this is just staggering to think about. All right, so dreaming big is great, but then reality hits you. And in space, reality is physics, and physics can be brutal. The very first and biggest challenge for any space mission is just getting off the planet and getting going fast enough in the right direction. So, how in the world do you travel between planets without needing an infinite amount of fuel? Well, the answer is something called the Hohmann transfer orbit. The easiest way to think of it is like the interplanetary superhighway. It's this really elegant, elliptical path that lets you just coast for most of the trip. You only need two big engine burns, one to blast out of your home planet's orbit, and another one to brake when you get to your destination. And this picture from the report shows it perfectly. See that? The spacecraft gets into a low parking orbit around Earth. Then it fires its engine, that's the first burn, to push itself onto that long, looping transfer orbit. Then it's just coasting all the way to the other planet, where it fires its engine again to settle into a new orbit. Now, the key phrase here is least energy. But here's the thing you gotta remember. Least in the world of space travel is still a colossal, almost unimaginable amount of energy. It's all relative. And this is where the rubber meets the road. This table from the 68 report puts actual numbers on it. This delta V is the change in velocity you need. To get to Mars, you need to change your speed by over 10 kilometers per second. For Jupiter, it's almost 19 kilometers per second. That's just the raw, unforgiving physics you're up against. Okay, so let's say you've somehow managed the launch. You've beaten the rocket equation. Congratulations. Now for the really hard part, the absolutely mind-numbing amount of time you have to spend on the trip. According to the report, a round-trip mission to Mars with a stopover would take on average 493 days. That's more than 16 months. Just think about that, stuck in a tiny capsule with a couple of other people for over a year. And if you thought that sounded tough, check this out. A mission to Ganymede, out by Jupiter, was estimated to take almost 4 years. 4 years! The psychological challenge of a trip like that is every bit as massive as the engineering one. So, how do you keep a crew of astronauts alive and healthy for that long out in the void? That's the real gauntlet. The engineers in 1968 had to think through every possible threat. First up, radiation. You know, space isn't empty. It's flooded with dangerous particles from the sun and from deep space. Once you leave Earth's protective magnetic bubble, you are getting blasted by this stuff constantly. This chart shows how much shielding you'd need, and it all depends on the sun's cycle. Without it, the mission's a non-starter. Then you have to worry about getting hit by tiny space bullets, micrometeoroids. And this table for a Jupiter mission is just fascinating. See, to shield against the expected amount of debris, what they call nominal, you'd need almost 2 million kilograms of shielding. But if you want to be safe against the worst-case scenario, that mass triples to over 6 million kilograms. So your entire ship design hinges on how much of a gambler you are. And of course, there's the most basic challenge of all, life support. You can't just pack enough water bottles and air tanks for a 4-year trip. It's impossible. You have to build a tiny, closed ecosystem right there in your ship and recycle everything. This chart from the report just lays it all out, plain and simple. It compares an open system, where you bring all your supplies, to a closed one that recycles. You can see pretty clearly that the longer the mission, the more the mass of that open system just skyrockets into absurdity. For a long trip, recycling isn't a choice, it's the only way. Okay, so you've figured out how to keep the crew alive, you've thought about all the dangers. Now, what kind of machine did they imagine you'd actually fly to pull all this off? Well, to get all that weight into orbit in the first place, you basically have two philosophies. You've got your expendable rockets, like the Russian Proton, that you use once and then they're gone, and then you have reusable vehicles, like the Space Shuttle was, which are designed to come home and fly again. And here they are, side by side. It's a fantastic visual. On the left, the throwaway workhorse, the Proton. On the right, the super ambitious and reusable Space Shuttle. These two pictures basically represent a fundamental fork in the road for space technology, a debate that is absolutely still going on today. And let's bring it all back to the core idea of this incredible 1968 report. It was all about finding those common requirements. They weren't just trying to design a ship to go to Mars. They were trying to create a systematic framework, a sort of master key that could unlock the entire solar system. The most important takeaway here is this. These engineers, working with slide rules and computers with less power than your watch, lead all the groundwork. They figured out the fundamental challenges of traveling in deep space. And those are the exact same problems that engineers at NASA and SpaceX and everywhere else are still working to solve right now. In the end, this incredible 1968 plan was a dream that got put on a shelf, mostly because of budget cuts and politics. And that leaves us with a really big question for today. What's it going to take to finally pull that 50-year-old dream off the shelf and make it real?